This is what we're leading up to in this video, an illustrated guide to one of the most beautiful theorems in modern math, the Fundamental Theorem of Galois Theory. At its heart, it's about creatures like this, algebraic equations, and what happens when you permute their inputs. This is a problem that's simple enough to state, but ends up using the full power of modern abstract algebra to deal with. Most people have heard of it because it leads to a proof that the quintic has no general formula in radicals. But this kind of math goes far beyond that one theorem. I honestly think it has the potential to change the way you look at numbers. Here's the plan for this video. First, we'll look at what this field studies by treating an example in non-rigorous language. Then we'll make things precise, introducing the basic tools of the subject, so-called fields and automorphisms. Then we'll look at the basics of group theory, and see how it reveals to us the underlying nature of these objects. Finally, we'll see how all these pieces come together in the Fundamental Theorem of Galois Theory. This theorem is without a doubt one of the crown jewels of modern math. But it all starts with a deceptively simple question: what is the square root of 2? You and I know that there are two answers to this question, the so-called positive and negative square roots of 2. The basic point of the video is this: there is no algebraic difference between root 2 and minus root 2. Anything quote-unquote algebraic you can say about root 2 will apply without change to minus root 2. For example, the fundamental property of root 2 is that root 2 squared equals 2. But that's also true for minus root 2. Minus root 2 squared equals 2. Say you have a more complicated equation like this that root 2 satisfies. If you cube it, you get 2 times itself. But again, it turns out, minus root 2 satisfies this exact same equation. In general, given any algebraic equation with rational coefficients, if you replace root 2 with minus root 2, it'll still hold true. You can fluidly pass between these two numbers, and the equation will never notice the difference. So to answer our original question, what is the square root of 2? Well, there are two such numbers. But they're not like any two other numbers you've seen before. In some sense, these numbers are like two copies of the same thing. This is a premonition of Galois theory. Some terminology that'll be useful. We say that root 2 and minus root 2 are conjugate over q. That means, whenever you have an equation with rational coefficients, replacing root 2 with minus root 2 will leave the equation holding true. The basic question of Galois theory is the following. Given a bunch of numbers that are conjugate over q, how many ways are there to swap them that preserve algebraic relations? What I mean by that is this. Suppose you're given an equation like this, involving root 2 and minus root 2. Does permuting root 2 and minus root 2 leave the equation holding true? In this case, the answer happens to be yes. And this is not obvious, but it's actually true in general. Given any equation with rational coefficients, swapping root 2 and minus root 2 leaves the equation holding true. Now, what we've seen so far are examples of two numbers being indistinguishable, but you can also have three numbers being indistinguishable. This is where things start getting interesting. Consider the complex number, which I'll write zeta. It lies 1/5 of the way around the unit circle in the complex plane. It's a fifth root of unity. This number has 4 conjugates over q, zeta squared, zeta cubed, and zeta to the 4th, equally spaced points on the unit circle like this. The fact that they're conjugate means that given an algebraic equation with rational coefficients, if I replace every instance of zeta with one of its conjugates, it'll still hold true. Now, suppose I'm given an equation like this, involving not only zeta, but the conjugates of zeta as well. Is it true that no matter which way I permute zeta with its conjugates, the equation will still hold true? No. The permutation I just showed you, for example, isn't actually allowed. This equation just isn't true. Likewise, this permutation doesn't preserve this equation either. It turns out that out of the 4 factorial, or 24 ways to permute these 4 numbers, there are exactly 4 that preserve algebraic relations. And not just any 4, these 4 over here. This means that whenever you have an algebraic equation with rational coefficients, applying these permutations will leave the equation still holding true. Now, it's not clear at this point why this is a question worth asking. I mean, wondering whether swapping root 2 and minus root 2 preserves algebraic relations is admittedly kind of a random question. The reason we're doing it is that if you look at the ways to permute a bunch of numbers that preserves algebraic relations, you can better understand how those numbers are algebraically related to one another. That's the basic content of the fundamental theorem, and that's what we'll see at the end of the video. Our example so far has been non-rigorous, to convey the basic idea of what's going on. Now our task is to make things precise. Our first job is to move away from talking about numbers and instead work with more flexible objects called fields. A field, roughly speaking, is any set where you can add, subtract, multiply, and divide elements. The rational numbers, for example, form a field. Importantly, you can't take square roots. If you want to talk about, say, the square root of 2, you have to enlarge your field to contain q and the square root of 2. Define q adjoin root 2 as the smallest field containing q and the square root of 2. It is closed under the 4 operations, so 1 plus the square root of 2 is in the field. So is 4 plus 2/3 square root of 2, and so on. Our next job is to move away from talking about permutations of numbers and instead talk about their abstract analogues, so-called automorphisms of fields. Here's the precise definition. If f is a field, an automorphism of f is a bijection, sigma, from f to itself, satisfying the following properties. First, sigma of x plus y equals sigma of x plus sigma of y, for all x and y in the field. And sigma of x times y equals sigma of x times sigma of y, for all x and y in the field. The intuition is that an automorphism is a function that shuffles around elements of the field while respecting the field operations. Some notation. The set of all automorphisms of f is denoted aut f. Unfortunately for us, this set is a little too big, so we're going to restrict our attention to a subset of automorphisms that satisfy an extra property. Namely, we say that sigma is an automorphism fixing q if sigma fixes q, that is, sigma of x equals x for all x in q. Again, some notation. Aut f over q denotes the set of all automorphisms of f fixing q. The intuition is that an automorphism fixing q is just a function that shuffles around elements of the field while preserving algebraic relations over q. Coming back to our framework, we first talked about the numbers root 2 and minus root 2. Now we're talking about the field q adjoin root 2. Before we talked about permutations of root 2 and minus root 2 that preserved algebraic relations with coefficients in q. Now we're talking about automorphisms of q adjoin root 2. And not just any automorphisms, but specifically the automorphisms fixing q. We will now look at 3 examples to get a feel for these definitions. Consider the field q adjoin root 2, which is the set of all elements a plus b root 2, where a and b are rational numbers. What are the automorphisms of this field fixing q? We can calculate them as follows. Take an arbitrary element of this field. Let sigma be an arbitrary automorphism and apply it to this element. Since sigma is additive and multiplicative, we can simplify the expression to get this. Here we also use the fact that sigma fixes q. So sigma is determined by where it sends root 2. Now we'll use a key fact that I haven't stated thus far. An automorphism sends each number to one of its conjugates. So it's either equal to root 2 or minus root 2. In the first case, this map sends a plus b root 2 to a plus b root 2, i.e. it's the identity. In the second case, it sends a plus b root 2 to a minus b root 2. So these are the two automorphisms of Q adjoin root 2 fixing Q. It's hard to visualize how sigma acts on the entire field at once, so we just draw how it acts on root 2, because that determines how it acts on the whole field. The first automorphism leaves every point where it is. The second automorphism swaps root 2 and minus root 2. These are the two ways to shuffle around elements of the field that preserves algebraic relations. In particular, this shows that whenever you have an equation involving root 2 and minus root 2 with rational coefficients, if you swap them, the equation still holds true, just like we claimed at the beginning. Now, it's not clear at this point why knowing the automorphisms is useful. We'll see that the automorphisms of this field are in some sense a mirror image of the field that they act on. So in that way, studying the automorphisms of a field allows us to better understand the field itself. That's the basic content of the Fundamental Theorem, and that's what we'll see at the end of the video. Before that, let's see another example of automorphisms. Consider the field Q adjoin zeta, defined as the smallest field containing Q in zeta, where zeta is a fifth root of unity, the complex number that sits on the unit circle 1/5 of the way around. This number has four conjugates over Q: zeta squared, zeta cubed, and zeta to the fourth, equally spaced points on the unit circle like this. As a set, it's the set of all elements of the following form. What are the automorphisms of this field fixing Q? Take an arbitrary element of this field. Let sigma be an arbitrary automorphism and apply it to this element. Since sigma is additive and multiplicative, we can simplify the expression to get this. Here we also use the fact that sigma fixes Q. So we see that sigma is determined by sigma of zeta. An automorphism sends every number to one of its conjugates over Q. So there are four possibilities for what sigma of zeta can be. There's one where zeta is mapped to itself, one where zeta goes to zeta squared, one where it's mapped to zeta cubed, and one where it's mapped to zeta to the fourth. Now you'll notice that I haven't drawn in the remaining arrows, and that's because they don't do what you expect. Take this one for example. Where does zeta squared go? Well, doing the calculation, we see that it's sent to zeta to the fourth. Now, doing a similar calculation for zeta to the fourth, we see that it's sent to zeta cubed. So in summary, we get this strange zigzag. If we follow the same procedure for the others, we get the following. What does this mean? In particular, this means that whenever you have an algebraic equation with rational coefficients, applying these permutations will leave the equation still holding true. It's sometimes helpful to see a non-example. So if you swap these two numbers, for example, you can check that this equation actually isn't true anymore. Likewise with this one. Again, it's not clear at this point why knowing the automorphisms of this field is useful. We'll see soon that using the automorphisms, we can uncover the internal structure of the field itself. That's the Fundamental Theorem, and it's what we're leading up to. Before that, let's see our final example. We'll again look at Q adjoin zeta, where now zeta is a 16th root of unity. Zeta has 8 conjugates in the complex plane, all odd powers of zeta. It is the set of all elements of the following form. What are all the automorphisms of this field fixing Q? Sigma is determined by where it sends zeta. An automorphism sends every number to one of its conjugates over Q. So there are 8 possibilities for where it can send zeta. There is one automorphism where zeta is sent to itself, one where zeta is sent to zeta cubed, zeta to the 5th, zeta to the 7th, and so on. Before I fill in the rest of the arrows, I want to emphasize there will not be a visually obvious pattern. With that, let's see what it looks like. Okay, I don't know about you, but my brain just cannot make sense of what it's seeing right now. The patterns seem almost random. But of course, it's not. This has a very concrete meaning. In particular, this means that whenever you have an algebraic equation with rational coefficients, applying these permutations will leave the equation still holding true. It's sometimes helpful to see a non-example. So if you were to say swap these two numbers, the resulting equation isn't true anymore. But even if this picture doesn't impress you, what we'll see soon is that the automorphisms of this field give us genuine information about the field itself. That's in some sense the punchline of this video. So to sum up, we've seen a bunch of cases so far. We've seen some fields with 2 automorphisms, fields with 4 automorphisms, and 8 automorphisms. The basic idea of Galois theory is to study a field via its automorphisms. At the start of the video, I mentioned that we would see some group theory. This is where it comes in. Because the true complexity of these automorphisms lies not in the automorphisms themselves, but in how they combine with one another. We will now see that they form a structure called a group, and that structure lies at the heart of the fundamental theorem. This is clearest if we just look at an example. If you apply this element, and then apply this one, the overall effect is the same if you just applied this. We can see this by following the arrows. For example, on this side, zeta goes to zeta squared. And on this side, zeta goes to zeta cubed, and then zeta cubed goes to zeta squared. On both sides, the overall effect is the same. Likewise, on this side, zeta cubed goes to zeta, and on this side, zeta cubed goes to zeta to the 4th, then zeta to the 4th goes to zeta. Again, the overall effect is the same. What I'm saying is that the set of automorphisms of a field is more than just a set. It is a group, where the group operation is composition of functions. You can combine these permutations with each other in any possible way. We'll arrange the results in a 4x4 multiplication table as follows. Okay, so we've seen that different fields have automorphisms fixing Q, and that these automorphisms form a group. But is any of this useful? This could give us no information for all we know. The point is that the automorphisms of a field form an exact mirror image of the field that they describe. That connection is spelled out in the fundamental theorem of Galois theory. We are now nearly ready to see this connection. To see that, consider the following situation. Suppose you have a field F containing Q, and you have a field K in between them. We started off looking at the automorphisms of F. We then restricted our attention to automorphisms of F fixing Q. Now we'll restrict our attention further to automorphisms of F fixing K. Each time, we add extra conditions the automorphisms have to satisfy, which makes the set of automorphisms we're considering smaller and smaller. As a concrete case of this, consider the field Q adjoins zeta, where zeta is a 5th root of unity. This contains Q. Sandwiched between them is the field Q adjoin the square root of 5. We started off by looking at automorphisms of Q adjoins zeta. Then we restricted our attention to automorphisms of Q adjoins zeta fixing Q. Now we'll restrict our attention once again to automorphisms of Q adjoins zeta fixing Q adjoin root 5. Phrasing this in a more down-to-earth language, we first looked at permutations that preserved algebraic relations over Q. Now we'll look at permutations that preserve algebraic relations over Q adjoin root 5. The example on the screen is an example of an algebraic relation with coefficients in Q adjoin root 5. Notice that this automorphism preserves this equation. While the other two automorphisms don't. So the automorphisms fixing Q are these four, while the automorphisms fixing Q adjoin root 5 are just these two. And with that, we can see our first glimpse of the fundamental theorem of Galois theory. On the right, I'll arrange the three fields we have in a tower. At the top goes Q adjoin zeta, then Q adjoin root 5. Beside Q, I'll place the automorphisms fixing Q. Beside Q adjoin zeta, I'll place the automorphisms fixing Q adjoin zeta, which by definition is just the identity. Beside Q adjoin root 5, I'll place the automorphisms fixing Q adjoin root 5. In words, these are all the ways to shuffle around elements preserving relations over Q. These are all the ways to shuffle around elements preserving relations over Q adjoin root 5. And these are the ways to shuffle around elements preserving relations over Q adjoin zeta. You might feel your heart rate picking up now. Every subfield on the right gets a subgroup on the left. But the surprising fact is that every subgroup is obtained in this way. There is a perfect one-to-one correspondence between subfields of this field and subgroups of its Galois group. These two worlds are exact mirror images of one another. With all that said, we can now state the fundamental theorem of Galois theory once and for all in its most abstract form. To do that, we'll need some notation. Aut f over q denotes the automorphisms of f fixing q. Here's the theorem. Let K be a field obtained by taking Q and adjoining finitely many algebraic numbers, alpha 1 to alpha n. And suppose K satisfies this technical condition. If alpha is in K, then all the Q conjugates of alpha are in K as well. Then there is a one-to-one correspondence between the subgroups of Aut K over Q and the subfields of K containing Q. That correspondence is given as follows. To any field L in between K and Q, assign to it the group of automorphisms of K fixing L. You might get the feeling that this is profound, but if you're anything like me, it's just so abstract that you can't see the message. There are many things going on here. For one, this side represents the structure of a field. It says what all the subfields are. This side represents the symmetries of the field. It gives all the ways you can shuffle around elements that leave certain equations unchanged. If I had to summarize this theorem in a sentence, it would be, the structure of a field equals the structure of its symmetries. But it's not just that these two sides look the same. One side is considerably simpler than the other. A field is an unfathomably complicated object. It has infinitely many elements, each with complicated interconnections with other elements. Whereas this group, it's a finite set. It just has 4 things in it. It is something you can hold in your hand and play with. The fundamental theorem of Galois theory allows us to distill the enormous complexity of this field into this tiny object, which, to be clear, is still complex, but it's a finite amount of complexity. Now we can look at our original question with a new perspective. What is the square root of 2? At the start of the video, our answer was that there are 2 square roots of 2, but they are indistinguishable over the rationals. But now you'll see something different. The answer to that question depends on the field you're living in. Depending on the field we're living in, permuting these 2 numbers may or may not preserve algebraic relations over that field. Those permutations form the Galois group, which by the fundamental theorem is a mirror image of the field it describes. So in that sense, the various answers to this question lead us to the fundamental theorem of Galois theory. That's all for now. With that, thanks for watching, and I'll see you next video.